Good afternoon, everyone. Today in this session, we'll be discussing about the tangential acceleration and angular acceleration and the total acceleration as well, right? We'll be discussing about both tangential as well as angular acceleration and the total acceleration. Before starting with the tangential and angular acceleration, we'll be discussing some of the questions, right? With respect to the topics discussed in the last lecture, right? So we'll be beginning with the question number one here. A particle is moving on a circular path of radius 5 meter and its time-dependent angular position is given as t cube minus t square, right? So particle is moving in a circular path of radius 5 meter and its a dependent angular position is given as t cube minus t square. Find its angular displacement in first 3 seconds, average angular velocity in first 3 seconds, angular velocity at t equal to 2 seconds, and angular acceleration at t equal to 2 seconds, right? These are the four quantities that we have to find, right? Four quantities. First of all, we have to find the angular displacement in first 3 seconds. So angular displacement, we know that it's the change in the angular position, right? It's the change in the angular position. That will be the angular displacement, right? So the first part of this question, that's the angular displacement. That will be nothing. That will be equal to delta theta. That's final angular position minus initial angular position. That's theta final minus theta initial, right? I can see here, theta has been given as a function of time, that's t cube minus t square, right? So at t equal to 0, the angular position of the particle on a path is equal to 0, right? At t equal to 0, right? So you know that angular position will be nothing. It will be t cube minus t square at time 3 seconds, t equal to 3 seconds, minus t cube minus t square, right? At time t equal to 0, right? So at time t equal to 0, the initial angular position will be 0, right? And time t equal to 3 seconds, the final angular position will be 27 minus 3 square, that will be 9, right? 9. So 27 minus 9, it has to be equal to 18 radians, right? So this will be the angular position after time t equal to 3 seconds now. Now let's talk about the average angular velocity in first 3 seconds, right? We have to find the average angular velocity in first 3 seconds. So the average angular velocity is nothing. That's delta theta, change in angular position, total change in angular position upon the total time, right? Now you can see in first 3 seconds, the change in angular position is 18 and the time is 3 seconds. That's equal to 6 radian per second, right? 6 radian per second, right? Now, similarly, angular velocity at time t equal to 2 seconds, right? Now, it's talking about the instantaneous angular velocity, that's omega, that's equal to d theta over dt, right? D theta over dt. That's equal to d over dt of t cube minus t square, right? T cube minus t square, that will be equal to 3t square minus 2t, right? Now, we have to find the angular velocity at time t equal to 2 seconds, right? Now, we can put the value of t equal to 2, right, in this equation. So it will be 3 multiplied by 4 minus 2 multiplied by 2, right? So it will be 12 minus 4, that's equal to 8 radians per second will be the angular velocity. Angular velocity at time t equal to 2 seconds, right? That's the angular velocity at time t equal to 2 seconds. Now talking about the angular acceleration, alpha, right? Angular acceleration alpha, that's nothing, that's t omega over dt, right? T omega over dt, right? So omega here is 3t square minus 2t, right? So it means t over dt of omega, that's 3t square minus 2t, has to be equal to 6t minus 2, right? 6t minus 2. That's the alpha, angular acceleration. Now substituting the value of alpha for to calculate the alpha, put the value of time t equal to 2 seconds in this equation. That will be 6 multiplied by 2 minus 2. That will be 12 minus 2. That will be equal to 10 radian per second square, right? So this will be the what we call as angular acceleration, right? Radian per second square, right? So we calculate the alpha, we calculate the change in angular displacement, we calculate the average velocity, angular velocity, as well as instantaneous angular velocity and instantaneous angular acceleration, right? Now let's talk about the second question, right? A disk starts from a rest and gains an angular acceleration, right? A disk starts from rest and gains an angular acceleration given by p is equal to 3t minus t square, right? 3t minus t square is the angular acceleration of this disk upon the application of a torque, external torque, right? Calculates its angular velocity after uh, time t equal to 2 seconds and angular displacement after time 2 seconds, right? We have to calculate its angular velocity after 2 seconds and angular displacement after 2 seconds, right? Now, alpha or the angular acceleration for this question is given as alpha is given as 3t minus bt square, right? It's 3t minus bt square. That's the angular acceleration, alpha, right? We have to calculate angular velocity after 2 seconds, right? We can write this alpha as d omega over dt, right? D omega over dt. That will be equal to 3t minus bt square, right? Not bt square, right? It is 3t minus t square. That will be 3t minus t square, right? Now from here, d omega will be nothing. That will be 3t minus t square dt, right? We can integrate it on both sides to calculate the omega, right? To calculate the omega. So a disk starts from rest. A disk is starting from rest. So at time t equal to 0, its angular velocity was 0, right? Right? So after some time t, it will have omega velocity, angular velocity omega, right? That's omega. That will be 3t square upon 2, right? Minus t cube upon 3. So this will be the angular velocity after some time t, right? Now we have to calculate this omega after time t equal to 2 seconds, right? So the omega will be here. Putting the value t equal to 2, it will be 3 into 2 square upon 2 minus 2 cube upon 3, right? That will be equal to 6 minus 8 upon 3, right? That will be 18 minus 8, that will be 10 upon 3 radian per second. This is the angular velocity for this particle after time t equal to 2 seconds. But we have to calculate the angular displacement also, right? After time t equal to 2 seconds, right? What we can do is that if we integrate angular velocity, we'll get the angular displacement, right? So integrating angular velocity, right? Integrating angular velocity, that's d theta over dt is equal to omega, right? That's equal to omega, right? Now integrating on both sides, that's dt will be equal to omega dt. If we integrate it, we'll get the angular displacement, right? Let's suppose at time t equal to 0, at time t equal to 0, there was some initial angular position theta initial, and after time t, there is some final angular position, right? Theta final, right? So theta final minus theta initial, this will be the angular displacement delta theta, right? That will be equal to integral of omega dt, right? Now omega has the value 3t square upon 2 minus t cube upon 3, right? Integrating it with respect to t, right? With limits 0 to t, right? 0 to t. So it will be equal to, so the integration of 3t square upon 2 with respect to t will be equal to t cube upon 2, right? It will be t cube upon 2, right? Similarly, integration of this t cube upon 3 will be t4 upon 12, right? This will be the integration, right? Now, after time t equal to 2 seconds, the angular displacement delta theta will be equal to, we put the value of t here equal to 2, right? It will be 2 cube upon 2, that will be 8 upon 2, that's 4. And it will be 2, 4, that's 16 upon 12, that will be minus 16 upon 12, that will be minus 4 upon 3, right? Minus 4 upon 3, right? So it will be 3 multiplied by 4, that's 12, 12 minus 4 will be 8. So 8 upon 3 radians will be the angular displacement here, right? So 8 upon 3 will be the final answer. 8 upon 3 will be the angular displacement for the time t equal to 2 seconds, right? So this is how we can calculate the angular displacement or angular velocity from angular acceleration, right? So what we can do is that what we can do is that if we have theta, right? If we have theta, so what we can do, if we do d theta or dt, right? If we take the first derivative of this theta, we'll get the omega, right? And taking the first derivative of this omega, we'll get the alpha, right? We'll get the alpha, right? Similarly, in the reverse direction, right? In the reverse direction, if we integrate alpha with respect to time, we'll get omega, right? And if we integrate omega with respect to time, we'll get the theta as a function of time, right? So this is how we can apply the differentiation and integration of the different quantities to find the unknown quantities, right? Now let's discuss this question. A solid body rotates about a stationary axis with an angular retardation k root omega. It's k root omega here, right? So it is k root omega. So k root omega is the angular velocity of body. Find time after which body will come to rest. If at time t equal to 0, angular velocity of body is omega naught. So it's given that at time t equal to 0, the angular velocity omega is equal to omega naught, right? This is the initial angular velocity at time t equal to 0, right? But there is an angular retardation that's given by k root of omega, right? K root of omega. It means that after some time, this body is going to come to at rest, right? So we have to find the time after which body will come to rest, right? It means its final angular velocity, or we can say final angular velocity will be equal to 0 when it comes to at rest, right? So angular retardation is given as k root omega. So alpha is given as k root omega, right? That will be equal to d omega over dt, right? D omega over dt. D omega over dt. Now what we can do is that if we integrate on both sides, that will be integral of k dt and integration of d omega over root omega, right? D omega over root omega. So its integration at time t equal to 0, right? Its initial velocity was omega naught, and after some time t, it has the velocity equal to 0, right? Because after some time t, the body comes at rest, disk comes at rest, the angular velocity comes to 0, right? Now we have to integrate this. We have to integrate this. The integration of this will be nothing. It will be equal to omega raised power 1 by 2, right? Divided by 1 upon 2, right? 1 upon 2, right? With the limits omega naught to omega, right? Omega naught to 0, right? Omega naught to 0, right? The limits omega naught to 0. You can see here. So it will be 2 root omega, right? It comes out to be equal to 2 root omega, right? 2 root omega. With the limits omega naught to 0, right? Omega naught to 0. So substituting the upper limit and the lower limit. So it will be 0 minus 2 root omega naught, right? 0 minus 2 root omega naught, right? And that will be equal to kt, right? That will be equal to kt. Now from here you can see here the time comes out to be a negative value, right? It means that the alpha here we had to take, it was the, we had to take alpha as minus k root omega because it was a retardation, right? If we take the negative sign of alpha here, right? We take a negative sign of alpha here, we'll get negative sign here, we'll get negative sign here, negative sign here, we'll be getting the positive sign here, right? It means that the time taken for this body to come at rest will be 2 root omega naught upon k, right? 2 root omega naught upon k will be the time taken by the body to come at rest, right? So this will be the total time taken by the body to come at rest. Talking about the next question, right? Talking about the next question, a grindstone starts from rest and has a constant angular acceleration of 4 radian per second square. The angular displacement and angular velocity after 4 seconds will respectively be, right? So it starts from rest. If the grindstone starts from rest, the omega naught initial angular velocity has to be equal to 0, right? And as a constant angular acceleration is a constant, that's 4 radian per second square, right? Per second square. The angular displacement and angular velocity after 4 seconds will be. So after 4 seconds, we have to find the angular velocity. We know that omega final is nothing. It's omega initial that plus alpha t when the angular acceleration is a constant, right? So initially it is starting from the rest, so omega naught is 0, right? So alpha is 4 multiplied by t, that's 4. So 4 into 4 will be 16, right? It is 16 radians per second, right? 16 radians per second. So this will be the angular velocity after time t equal to 4 seconds, right? Similarly, talking about the angular displacement, right? Angular displacement, we know omega final square, right? Omega final square is equal to omega initial square plus twice alpha delta theta, right? Twice alpha delta theta, right? Twice alpha delta theta. Now you can see that omega naught square here is equal to 0, right? So this is twice alpha delta theta, right? Omega naught square here is 0, right? It's 0. So omega final we got equal to after time t equal to 4 second, that's 16, right? It will be 16 square, right? Upon 2s alpha, right? That will be the angular displacement delta theta, right? So from here delta theta will be 16 square upon 2 multiplied by 4. That's 8, right? It will be 16 multiplied by 16 upon 8. So it will be equal to 32, right? 32 radians. So 32 radians will be the angular displacement here, right? For time t equal to 4 seconds. We use the equation of circular motion here, right? Because angular velocity, angular acceleration here was a constant quantity, so we can use the equations of motion for circular motion, right? Now talking about this question, the figure shows the angular velocity versus time graph of a flywheel, right? There is a flywheel. The graph for the angular velocity versus the time graph is given, right? The angle in radians through which the flywheel turns during first 25 seconds is, right? So the question is that we have to calculate the angle through which the flywheel will turn during the time t equal to 25 seconds, right? So during 25 seconds, we have to calculate the total angle turned by this flywheel, right? Now we know that omega is nothing, that's t theta over dt, right? T theta over dt, right? So d theta, if we integrate it on both sides and integrating omega with respect to time, right? So theta 1 to theta 2, right? Theta 2. So this is nothing, this is the delta theta angular displacement, right? This is nothing, this is delta theta angular displacement, right? Angular displacement. This is angular displacement. It also represents area under omega t graph, right? Omega t graph gives the displacement, angular displacement, right? So the area under angular velocity time graph gives the angular displacement, right? Similarly, here we have been given the graph between angular velocity and the time. So if we calculate the area under this angular velocity time graph, we come to know about the total angle in radians through which the flywheel turns during 25 seconds, right? So this area we have to calculate, right? We have to calculate this area, right? You can see it's a trapezium, right? It's a trapezium. And we know the area of a trapezium is nothing. It's half sum of parallel sides. So this side and this side is a parallel side. From here to here, the distance is 25, right? Plus, and from here to here, the distance is 20 minus 5, right? That's equal to 50 multiplied by the distance between them. So this is the perpendicular distance between them. That's 30, right? So multiplying it with 30, right? So A will be equal to half 40 multiplied with 30, right? So that will be equal to 20 multiplied by 30, right? 20 multiplied by 30. That will be equal to 600 radians, right? 600 radians. It means this is the total angle through which this flywheel will turn during the time t equal to 25 seconds, right? 600 radians. So let's talk about the relation between the tangential, radial, and linear acceleration, right? All the relations will be discussed here, right? We know that velocity vector is nothing that's equal to omega vector crossed with the position vector of the particle, right? We can write v is equal to omega cross r, right? V is equal to omega cross r. Now, if we take the derivative of this velocity vector, right? derivative of this velocity vector, this will give us the total acceleration, right? This is nothing, this is the total acceleration. So derivative of this velocity vector will give us total acceleration, right? Total acceleration. Now, if we take this derivative on both sides with respect to time, that's dv over dt, right? That will be equal to d over dt of omega vector cross r vector, right? How can we take derivative of it? The derivative will be taken d omega upon dt, then crossed with r vector, right? Plus omega vector crossed with dr upon dt, right? So this is the total derivative of this velocity, right? As a function of time. So this is the total acceleration, right? Now we know this d omega over dt is nothing. D omega over dt, that's alpha, right? That's alpha. So alpha cross r vector, right? Plus dr over dt, that's v. We left with omega cross v vector, right? I can see here, this is a total acceleration. So dv over dt is the total acceleration here, right? And it has two components. One is alpha cross r vector, right? Another component is omega cross v vector, right? Omega cross v vector. Now this component we call it as alpha cross r. This is what we call as alpha cross r vector. This is one acceleration and this is another acceleration, right? This acceleration we call as tangential acceleration. That's omega cross v, right? This is tangential acceleration, right? And this acceleration we call it as radial or centripetal acceleration, right? Radial or centripetal acceleration. So these are two accelerations here, right? The total acceleration is actually the vector sum of the two accelerations here. One is the tangential acceleration and other is the radial acceleration or centripetal acceleration, right? So alpha cross r is nothing, it's the radial acceleration, right? Alpha cross r, that will be a radial, right? And omega cross v will be equal to tangential, that's a tangential, right? Now the total acceleration here will be total acceleration a total will be nothing, it will be the vector sum of both. Both acceleration, tangential and radial acceleration are perpendicular to each other, so their total acceleration will be tangential square plus radial square, right? So this will be the total acceleration for this particle, right? Total acceleration for this particle. This radial acceleration we can write alpha is omega upon r, right? Alpha is perpendicular to r, so it will be r alpha, right? A will be r alpha, right? Or we can write it equal to alpha r, right? We can also write this radial acceleration as v square upon r, right? This will be equal to v square upon r, right? That's alpha r or v square upon r. This will be the radial acceleration, right? And omega cross r vector, right? We know omega and v vector will be once again perpendicular. That will be equal to omega into v, right? Omega into v, right? We know v is equal to omega is equal to v upon r, right? Omega is equal to v upon r, right? V omega is equal to v upon r. It will be v square upon r, right? This is what we call as a radial acceleration, right? This is nothing. This is radial acceleration, right? This is nothing. This is the radial acceleration, right? Or centripetal acceleration, right? So we have two components here, right? One is the radial acceleration, radial component, and another is the tangential component, right? So this is the tangential component here, right? This will be the tangential component. This is the tangential component, right? This is tangential, right? And this is the radial component. So this is the tangential component and this is the radial component here, right? So alpha cross r will be the tangential component and omega cross will be the radial component, right? So the total acceleration will be tangential square plus radial square, right? So it means that we can write this total acceleration as A total, that will be under root of V square upon R whole square, right? Plus R alpha whole square, right? So this will be the total acceleration. This is nothing, this is the total acceleration, right? This is the total acceleration. Or we can say that dv upon dt, right? If we take the derivative of speed with respect to time, modulus of v vector is nothing, mod of v vector is nothing, that's the speed, right? Mod of v vector is nothing, that's speed, right? If we take the derivative of the speed, this will give us the tangential acceleration. It means it's the rate of change of speed tangentially for the particle moving in a circular motion, right? This is the tangential acceleration. Tangential acceleration, right? And this is the total acceleration, right? This is nothing, this is total acceleration. So this will be the total acceleration. So there is a difference between the total acceleration and tangential acceleration. So radial acceleration is omega cross v, that's equal to v square upon r, right? And tangential acceleration is alpha cross r vector, right? That will be alpha, right? Or we can say alpha angular acceleration will be tangential acceleration upon the r, right? So this we can use, right? I will be using this in rigid body dynamics as well, right? In the rotational motion, this will be also used in the rigid body dynamics, right? This equation, right? The relation between the angular acceleration and the tangential acceleration, right? Now I'll be discussing this question, right? A particle travels in a circular motion of radius 20 centimeter at a speed that uniformly increases, right? A particle travels in a circle of radius 20 centimeter at a speed that uniformly increases, right? So the particle is moving in a circular motion of radius 20 centimeter, right? At a speed that uniformly increases. If the speed changes from 5 meter per second to 6 meter per second in 2 seconds, find the angular acceleration, right? So the angular acceleration will be nothing. It will be the tangential acceleration upon the r, right? The tangential acceleration will be nothing. What will be the change in speed at 6 minus 5 upon in 2 seconds, right? This will be the tangential acceleration upon the radius. That's 20 centimeter. We can write it as 0.2. So it will be 1 upon 0.4, right? That will be equal to 2.5, right? Radians per second square. 2.5 radians per second square. This will be the angular acceleration for this particle. Now, talking about the next question, a particle moves in a circle of radius of 0.5 meter at a speed that increases uniformly, right? Find the angular acceleration of the particle if its speed changes from 2 meter per second to 4 meter per second in 4 seconds, right? So the radius of this circle here is given as the radius of the circle in which the particle is moving. It's given as 0.5 meter, right? 0.5 meter. The speed of this particle increases uniformly, right? So it means that there is a tangential acceleration, right? Find the angular acceleration of the particle if its speed changes from 2 meter to 4 meter per second square in 4 seconds, right? So the alpha will be nothing. It will be the tangential acceleration upon the radius, right? Tangential acceleration here will be the change in speed per unit time, that is 4 minus 2 upon in 4 seconds, right? That will be 4 multiplied by the radius, right? Radius is 0.2, 0.5, right? 0.5 meters the radius, so it will be 2 upon 4 multiplied by 0.5, right? That will be equal to 2 upon 2, that will be equal to 1 radian per second square, right? So this will be the uh, tangent, this will be the angular acceleration, right? This is the angular acceleration for the particle, right? Now talking about the second question, right? The second question is that a particle is revolving in a circular path, right, of radius 500 meters, right, at a speed of 30 meter per second, right? A particle is revolving in a circular path of radius 500 meters at a speed of 30 meter per second. It is increasing its speed at the rate of 2 meter per second square, right? What is its acceleration, right? So if the speed is increasing at the rate of 2 meter per second square, it means the tangential acceleration here is 2 meter per second square, right? This is the tangential acceleration, right? Now talking about the radial acceleration or the centripetal acceleration, right? Centripetal acceleration. Now you can see here, centripetal acceleration will be v square upon r, right? V square upon r, right? A particle is revolving in a circular path of radius 500 meter at a speed 3 meter per second, right? It is increasing its speed at the rate of 2 meter per second square, right? What is its acceleration, right? It's talking about the total acceleration, right? Total acceleration, a total will be nothing. It will be under root of tangential acceleration square plus the radial acceleration square, right? We're talking about the radial acceleration, right? Radial acceleration. At an instant, its speed was 30 meter per second, right? And it was increasing at a speed at the rate of 2 meter per second square, right? So the radial acceleration here will be nothing. It will be v square upon r, right? At this instant, the radial acceleration will be 30 square upon the radius, that's 500, right? That will be 900 upon 500, right? That will be 9 upon 5, right? 9 upon 5, right? Now, total acceleration here will be, that will be tangential plus tangential square plus the radial square. That will be 9 upon 5 whole square, right? So this will be the total acceleration for this particle, right? This will be the total acceleration for this particle. That will be under root of tangential square plus the radial square, right? Now let's discuss this question. This is the last question for this session, right? The question is that a particle is performing circular motion of radius 1 meter. Its speed is given as v is equal to 2t square, right? The particle is performing circular motion of radius 1 meter. Its speed is given as v equal to 2t square meter per second. What will be the magnitude of its acceleration at t equal to 1 second, right? We have to find the magnitude of the acceleration at t equal to 1 second, right? There will be two accelerations. One will be tangential and another will be uh, centripetal, right? So the tangential acceleration will be dv over dt, right? Because it's a speed as a function of time, right? It will be 2 times the derivative of t square with respect to t will be 2t. That will be equal to 4t, right? 4t. So at time t equal to 1 second, right? 1 second, the value of the tangential acceleration will be 4 meter per second square, right? 4 meter per second square, right? Talking about the centripetal acceleration alpha, that will be equal to centripetal acceleration here will be a radial, that will be equal to v square upon r, right? V square upon r. So v square upon r. V square is equal to 4. It will be 4 square upon r. R has the value equal to 1 meter, right? So it will be 4 square upon 1. That will be equal to 16, right? So 16 here is the radial acceleration. The total acceleration here will be equal to under root of total acceleration here will be under root of tangential acceleration square, that will be 4 square plus the radial square, that will be 16 square. So this is the total acceleration of the particle, right? This will be the total acceleration for the particle, root of 4 square plus 16 square. This is the total acceleration, right? So this is how we can calculate the angular acceleration. This is how we can calculate the tangential or radial acceleration or the total acceleration for the particle, right? So the total acceleration in a circular motion is there are two accelerations in a circular. There can be two accelerations in a circular motion. One is tangential acceleration, and another is radial acceleration, right? Radial acceleration is always present in a circular motion because radial acceleration continuously changes the direction of the velocity vector, right? And the tangential acceleration increase the speed of the velocity, increase the speed of the particle in the tangential direction. That's the tangential acceleration, right? And the question is that in a uniform circular motion, the velocity is a constant, the speed is not changing, the tangential acceleration is zero, right? In uniform circular motion, or we can say that the only acceleration present in the uniform circular motion is the radial acceleration, and this radial acceleration continuously changes the direction of the velocity vector, right? So that's it today, right? We'll stop here. We'll be meeting in the next lecture with the rigid body dynamics or the rotational motion. So till then, take care and goodbye.